bem curto. Então, na última aula, o que a gente provou? Eu não lembro. Right. So I'm just saying that this is going to be a very short class, unless we digress on something else. But yeah, so last time, what we did, recap. We talked about exactness of hom and P being projective. And we talked about resolutions. Particularly if you give me an object A, we talked about taking a projective resolution. Like this. Okay. And the important theorem we proved last time is that if we have, well, no, actually, it's less than just having enough projective. We just, the theorem is, well, we proved two theorems, is that if the category A has enough projective, that means for every object A, there exists a projective object in the category and a surjection to A, then we can construct resolutions. And for every object A, we have a projective resolution. Pk minus 1 to P1 to P0 to A 0. And this is an exact sequence. So this is theorem 1. And theorem 2 was that this resolution was somehow universal. So theorem 2 was that projectives are nice to, it's easier to map out of projectives. It's easy to map out of a projective. And if you take a projective resolution of something, so again, Pk to Pk minus 1, P1, P0, A, and you have any other object, P, and a resolution of this object, and you have a morphism in your category F, then this is for any resolution. Then you can lift. These guys exist. This is F0, F1, F2, Fk minus 1, and Fk, making these diagrams commute. And the Fi's, so they're not only a lifting of F, meaning that they make every diagram commute, but these F stars actually are unique, up to unique homotopy. So a unique chain homotopy. Namely, if you give me any other lifting, we constructed an explicit homotopy from F to your other lifting. And actually, we needed less than this. We needed just that the PIs just needed these are projectives. We didn't need the fact that this was a resolution. We never used the fact that not necessarily a resolution. So not even necessarily a complex. So we only used the fact that each one of these p's was projective to construct the homotopy maps. So to construct these maps in this direction to construct the chain homotopy. Okay, so that was what we did last time. And I think I rushed through a couple of results. So one of them was that we started digressing into what is a projective complex in the category of chain complexes. But I think I went too fast. So I can take a complex built out of projectives. So let's suppose that this is a complex, is a chain complex, say of R modules or whatever it is, where each pk is projective. But it might not be that the complex itself is projective in the category of complexes. But p dot may not be projective in chains. Indeed, let's suppose that p dot is projective. And let's take this to be in chains bounded below, above.
So the definition of resolution asks for the family of maps to be a complex or to be exact?
So a resolution is, so caveat, a resolution, so definition, let A be an object in a category. A resolution of A is a complex no, let's not use the word P. It's a complex C dot, which is in chain complexes bounded below in the category A, together with a map. So this is a complex. This is bounded there. So this means it's a complex that just may star, may not star. It has some ck, going to ck minus 1, so forth, c1 to c0, and then to 0. So requiring that this guy is bounded below. And so it's a complex together with a map of complexes. So I can also look at the complex A, which has 0 everywhere else. So the differential is 0. And I want to have a map of complexes. Which is a map of complexes. And moreover, I will require that the homology and the homology in degree n of the complex C is equal to A if n is equal to 0. So concretely, Z0 modulo the image of this differential is A, 0 if n is not 0. So in other words, look at the extended complex. Since this homology is A, and the homology by definition is a quotient of C0, then I have a natural map which is from epsilon that goes from C0 to A. This map has to be surjective because I want a quotient of C0 to be isomorphic to A. That means that this epsilon here needs to be surjective. So I have this map surjective. On the other hand, the homology in degree 0 is the kernel of this map divided by the image of this map. And I'm declaring that to be isomorphic to A. So that means that now this guy became exact. So if, oh, I'm sorry, the kernel of this map, which is 0, divided by the image of this map was A. So that means that now that the kernel of this map is equal to the image of this map. So now this complex here, which is extended, became exact because the kernel of this map was already equal to the image of this map by this condition. So this is equivalent to having a resolution. That this extended complex is exact. So that's a resolution. All right. So now, what we proved is that for every object in a category where I can choose a surjection from a projective guy, for example, the category of R modules, we can always find a resolution, and we moreover find the resolution where each one of these CIs is projective. But there's an extra question, whether or not a complex is projective in this category. This category is an abelian category, so I can ask whether or not an object is projective in that category. Namely, Holmes from that guy is exact. That's the definition of being projective. Is the home from that object into any other object of that category exact? And again, home is always left exact, so this question is a question of whether this functor here is right exact, namely whether this functor preserves surjections. So now let's suppose that we have a complex that is exact in chains, which is a I'm sorry, not exact. Let's suppose that we have a complex in chains that is projective. Okay. So this means this guy is a projective object of this category of chain complex. Then, well, remember we have the following datum. I can take this guy and I can map it by the identity to P. Well, we can take the cone of the identity map and we didn't have this. What we had is this shifted by -1. So I can just put the identity map here. Remember, for a map of complexes, if we had a complex C and a complex D, let's write it like this, a complex C, a map F to a complex D, we constructed a long time ago a map from the cone of F to D shifted by to C shifted by -1, an exact sequence of complexes. And we use that to construct this delta functor. So, okay, so in particular, I can take C is equal to P. And I get a map from the cone, an F to be the identity. C is equal to D is equal to P, and F to be just to be the identity of P. So therefore, I get a map from the cone of the identity to P shifted by 1. And this is surjective. And then if this guy is a projective object, this gives me a map like this. And this map is a lifting of this identity. That means that this composition here is the identity. So that's the same thing as just picking a lifting, a splitting of this surjection, whose kernel was P. This sequence is exact. So if I take C is equal to D is equal to P, the kernel of this map is P. So that means that this guy here makes the cone of the identity into a direct sum of P plus P dot shifted by -1. But now let's concretely see what that is. Modulo signs. So modulo signs we had chosen when I had this map from C to D, which was my f. I put cone of f. Well, this was a sum of these two things. I think the way I'm doing this, I'm putting this guy in degree 1 less, and this guy keep it in degree 0. So I took D plus C shifted by minus 1. I think probably I'm shifting in the wrong direction here. Just dyslexic here. But anyway, so the point is that this thing here has in degree n, I want it to be dn plus cn minus 1. And the differential, probably let's do degree n plus 1 to be this. Yeah, so I'm writing the differentials in the wrong order here. Because I'm just too used to homological complexes. So the map should go from cone of this guy, which I'm writing this as dn plus cn minus 1. And, well, here I have a map, which I think I'd use this sign. Here I have a map which is minus the differential in C, and here I have a map which is F, but I took it to be minus F. I think this is the sign convention that the book used. Okay, now what I'm saying is that in this particular case that I'm choosing a lifting, okay, I'm looking at F being the identity, and what is this map? Well, this map is from P shifted by minus 1 to the cone of the identity of P. So now I look at what is this guy in degree n. And I look at what is this guy in degree n. So this guy in degree n is P n minus 1. And this guy in degree n, well, I see it here, is D, which is P n. And then plus P, C, which is also P in degree n minus 1. So what I have is a map from here to here, which also lifts the natural map from Pn to the cone of the identity. So I have a map from Pn to here, which is just the inclusion, is the identity isomorphism here. And this is the inclusion here. Oops. Yeah. So I'm just writing this guy as a direct sum of these two. However, this is an exact sequence of complexes. So this guy as a direct sum of two complexes has a differential where this map here, F, does not appear, which is the identity. So that's really the lifting that goes from Pn minus 1 to Pn. So what we just constructed is the splitting that gives us that if P is projective, in chains, then it's split exact. Well, not only I gave you the splitting, but I just told you that the F is just trivial. It was the identity, it's just the same thing as not having that differential. Okay, so, and this is an if and only if. If you have a complex that is split exact, then prove that it's projective. That's an easy consequence in the other way around. So if you have a complex that is built out of projectives, that is split exact, then prove that it's projective in the category of complexes. That means if you have any surjection of complexes and a map like this, then you can map it to the other side. And this is very simple because, well, I'll let you as an exercise. The fact that each one of these terms is projective is going to allow you to produce the maps of modules, and then you need to check that it commutes with the differential. That's where you're going to use discrete exactness. All right. Okay, so essentially that was as much as we did last time. And there's not much that we're going to do today. So let me tell you what we'll start doing today. So we'll talk about derived functors. I'm not going to do much. I'm just going to define them in the case where we have enough projectives. I'm going to state a couple of things and then we'll solve. So let's suppose that you have f, a functor of abelian categories from A to B, that is right exact. So it preserves surjections. And let's suppose that A has enough projectives. Then let me define the left-derived functors, Lnf. These are going to be functors from A to B for each n bigger or equal than 0. And they're going to be defined as follows. So you start with A. In A, you choose a projective resolution that we know they exist because the category has enough projectives. So you choose a projective resolution of A. And now you define Ln Lnf applied to A is the functor f applied to Pn in that resolution. Actually, oops. Take the resolution and take the nth homology of that thing. That more or less worked, but not exactly. Okay, so this P is the complex. Okay, so that gives you that's almost a definition. Let's check that this is well defined. Okay, so I need to check that this thing does not depend on the projective resolution that I've chosen. That's the first thing. So first statement, this is well defined. And then there's a bunch of things that we need to check. So let's check first that it's well defined, at least as an object in P. Okay? So, well, let's take another resolution. So I have A, and I have my P0, P1, P2, etc. And I have A, and I take another resolution, Q0, Q1, Q2, etc. Now, I can take the identity map between these two guys. And the comparison theorem tells me, since this is a projective resolution, that I can extend this way. So I can extend this uniquely modulo a chain homotopy between these two guys. So F1, F0, F1, F2, etc. So now let's apply the functor f. So what is this? The rule of computing this guy is I apply my functor f to the complex. So I apply f to everywhere. So I have f of a, f here, f here, f here. And now I need to apply f to this guy, f to this guy, f to this guy, f of the identity here to fa, So this is the identity of f of A. And now I have f of q, f here, and everything commutes because my f was a function. Okay? So I have these guys, and they lift this identity of f of A. But now this guy, q, was also a projective resolution. And I also have the identity, well, I'm going to do this with fa. Well, I'm going to go back there. fp0, fp1, p2, etc. Now these guys commute. Now the composition of these two guys is a lifting of this identity map. Right? So I have here the identity of f of A. I could do this without the f's too. Let's forget about the f's everywhere, and I would have a lifting of the identity of A, which is given by a composition of two liftings. Okay? One from P to Q0, and then Q0 to P0 again, or P1, Q1, and then Q1 again. And this composition is a lifting of the identity. And we have one lifting, which is the identity. The identity lifts the identity, and we know that whatever lifting we choose is unique up to homotopy. So we know that this F1 was unique up to, well, this series, F0, F1, F2, etc., was a map of complexes that was unique up to chain of homotopies. This series of maps, G0, G1, G2, etc., is also unique up to a unique chain homotopy. So the composition is unique up to a unique chain homotopy. This means that these two maps, the composition of these two guys, Fn composed with Gn, the other way around, this is a sequence of complex maps from Pn to Pn, is homotopic to the identity. And the same way the other way around. So the same argument tells you that the composition Fn-Gn is a map, is a complex map that is a map from Q, complex from the Q to Q, is also chain homotopic to the identity of Q. So now I have a map of complexes from P to Q, okay, and a map of complexes from Q to P that are that induce the same maps on cohomology. So therefore, when I apply F, I'm going to get the identity applied to Fs. So I'm going to get the same homologies on these complexes after I apply Fs. I could do this on over F of A. Okay, so this thing is well defined. Well, not really. What we've defined is an object of the category B. I need to check that this is a functor, that these are functors. So Ln f of A is a functor. Well, you give me A, you give me B in your category, and you give me a morphism. And then again, same business. You choose a projective resolution of A, you choose a projective resolution of B. You do get a lifting unique up to unique homotopy. You apply F. I'm slow here. So this is F of F, and this is F of my lifting. I get this complex, and I get this complex. And now I take homology. Homology is a function. So this gives me a map from Hn F of P to Hn F of Q. Now this is Ln of B, Ln F, the left-derived functor n times of F applied to B, and this was by definition the left-derived functor of F applied to A. So I've gotten a map from here to here. So that's what I will define as, this map here is what I will define as Ln F of little f. Well, was there a choice here? No, because if I change my lifting f by another lifting, I know that they are chain homotopic. Therefore, when I apply f, they induce the same map in homology. They might be different maps, but in homology they are the same. So this guy is unique, even though the lifting is not unique. Okay? Once I pass to homology, this map is unique. So that's important that we take homology here. That map is compatible with compositions. And that's clear now because the compositions of the lifting is unique up to homotopy, so up to a unique homotopy. Namely, if I continue this thing, let's put a different color so not to make it more confusing, but I don't want to repeat the same diagram all over again. If I continue this guy by picking a G from B to C, so this is f of some G. Here G is a map from B to C. Then you pick a resolution of this C. I don't know, P, Q, R. I get this. And then again, this was a lifting G dot. And I get f of this. And now this composition is not unique because it may differ by choosing a different map lifting f here and a different lifting j here. But this composition is unique up to a unique homotopy, chain homotopy. Therefore, when I pass to homology, this composition is unique. Therefore, it has to be equal ln f. And then I compose this with ln g. This has to be equal to ln, f. I'm deriving f of g composed with f. Just because they both are liftings, and these are well defined up to a unique chain homotopy. Okay, so we get this, and of course the identity goes to the identity. So that means that this guy is compatible with compositions. That guy is a function, yes?
You are not using the uniqueness of the homotopy, just the existence.
I am not using uniqueness of the homotopy here, just the existence.
It's true at all, because in the true, you just use the top arrow ignore projected resolution. So you have some homotopy, but you essentially talking about projective resolutions don't give you any uniqueness.
Oh, wait, so you might be, so what's the statement here? So yeah, I might be screwing up this. So the statement is that if I choose any other lifting, these two guys are related by a unique homotopy. That's what I'm claiming. And you're saying that that's false.
Yeah.
That's interesting. So let's see.
There is a homotopy.
Yeah. Yeah, I might have many null homotopies in the yeah. So Tadeu is absolutely right. So this is something I got wrong. When I made this construction, I've used that Pn was projective to construct this guy, essentially because the argument here was like this. We proved that we could find a lifting. We had one lifting, and then we say, well, let's choose another lifting. I'm going to I want to construct these splittings such that this plus, taking d here to Pn minus 1, plus this is this map here. Okay, so how did we do this? Well, we restricted this map to the image of this differential so that this guy becomes surjective. And once that we have this guy surjecting, we can pick a lifting here. And we didn't lift this map, but we lifted this map minus d composed with s that we assume constructed by induction. So we assume that this part of the diagram was constructed, and then we picked a lifting here. But the question is, was this map unique or not? And yeah, the answer is no, of course, because this guy was surjective. I could just choose any other lifting here. Yeah, so Tadeu is absolutely right. Whenever I've been saying up to a unique chain homotopy, that's false. Thanks. So in other words, we could have several chain homotopies to the zero map. between these complexes. For example, if Q is 0, I can pick a lot of chain homotopies. Probably if P is 0. No, that's probably unique. Yeah. But if Q is an exact complex, which is 0 in homology, then I can just pick essentially anything, and that's going to work. Yeah, so that was certainly wrong. Okay. Anyways, I'm only using the fact that I have that any two guys are connected by a homotopy. Therefore, in homology, they are unique. That this map is important. That is unique. That ln of f is unique. This unique is true and is important. Yeah. Okay. So we have that this ln of f, this derived functor, is a functor. Let's check that it's additive. But this is obvious. So ln f is an additive functor. Well, this is essentially the fact that if you have, well, let's write it. At the level of objects, if you grab two guys like this, and you have a projective resolution of P is a projective resolution of A, and Q is a projective resolution of B, then the direct sum is a projective resolution of A plus B. So if I apply F to this F to P plus Q, since F itself is an additive functor, this is the same thing as F of P plus F of Q. And therefore, if I take homologies here, it's the same thing as taking homologies here. And the homology commutes with direct sums. So this is the homology of f of p plus the homology of f of q. So taking the degree n part, you get that the ln of f of a plus b is the direct sum of ln f of a plus ln f of b. On the other side, for morphisms, if you have a morphism from a to b, f, and you have a morphism g from a to b, the way we constructed this guy here, ln of little f, was by choosing this projective resolution of this guy, P, choosing a projective resolution of this guy, Q, choosing a lifting of our f here, and applying f, the functor f to this. But now if I have a lifting of f and I have a lifting of g, then their sum is a lifting of f plus g. So f dot plus g dot is a lifting of f plus g. So that means that, well, I'll just take the sum as a lifting of f plus g, and then by construction, ln f of f plus g becomes ln f of f plus ln f of g. So the functor is additive. Okay, so we define some additive functors, which are the derived functors of the right exact functor f. Why did I need that guy to be right exact? So theorem, ln f delta that we haven't constructed is a delta functor. Okay, so what this includes? This includes the fact that if you have a short exact sequence like this, then we want to get a long exact sequence, L0, C, 0, 0B, 0a. These are all derived of a fixed functor f. L1 derived of f of c. L1 derived f of b, and so forth. So in general, we want to go from Lk derived of f c to Lk minus 1 derived of a. And this is exact. So what we need to construct is these guys. Oops. Okay? So the first observation is that this is f. And here we'll use the fact that f was right exact. Perhaps a couple of observations. Since we've proven that these derived functors did not depend on the chosen resolution, so I don't know, observation, since ln f of A does not depend on P, just the fact that it exists, well, in particular, if A is projective, I can take it as a resolution itself. If A is projective, then Ln of A is equal to A if n is equal to 0, and 0 if n is non-zero. So if I have a projective resolution, Ln. Well, actually, let's prove that, because I haven't really proved this yet. What I'm proving is that lnf of A is 0 if n is equal to non-zero. That's clear, because the projective resolution is going to have 0 away from degree 0, if I take A to be projected. But I haven't proven that lnf of A is, actually, this is f of A. So let's prove that. So what is missing here is that L0f of A is equal to f of A. But that's clear because what I did is I've taken a resolution. And I am applying f, which is right exact. So this guy is still surjective. So if I just take this k1 I replace by the kernel, then I could just put here an f of k and still be exact here. Okay? So the point is that this sequence is still exact at this point, because f was right exact. So instead of taking P1 here, you can take the kernel, for example, of this map. And now apply f to that. This is going to be f of k. And, well, I cannot put a 0 here because f is right exact, not left exact. But this sequence is still exact. So it's still exact at this point. So the kernel of this map is equal to the image of this map. Okay. So, okay, again, the kernel of this map is still surjective. And the kernel of this map is equal to the image of this map. Now, this guy divided by the image of this map, well, I'll let you to check that. You get a map, you get an isomorphism from there, from H0 of f of P. It's isomorphic to f of A. this guy here, since this sequence is exact, is still the co-kernel of this divided by the image of this map. Okay? I cannot say that this is equal to this divided by this because this might not be injective. But it's still this divided by the image of this map, which is saying the thing as this divided by the kernel of this map, which is f of a by definition, because this map is a surjective map. Okay, so this implies that this guy here is L0 f of a. And this holds for every a. In particular, when a is projective, then we get this identity there. Okay, so in this long exact sequence, I can replace these guys by f of c, f of b, f of a, and then I need to take the first derived functor of f here, and I want to compute this delta. Okay, so how are we going to compute these deltas? So how to produce and we can probably stop there. All right. So what I'm going to do is I'm going to produce projective resolutions of these three guys. And I'm going to get a short exact sequence of complexes. And when I have a short exact sequence of complexes, I can just take homology of those complexes. Now the trick is that there's going to be a technical point that I don't want to do again the diagram chasing. But let's phrase it as a lemma, and then we may have time again in the end and do it. But take a projective resolution PA, probably PA of A, and PB, PC of C that we have. Then there exists a projective resolution PB of B such that we have a short exact sequence PA, PB, PC. In chains. This is not hard to do. We can do this by induction, starting from the zeroth projective guys and using a lifting, using the fact that the guys that you've chosen in C, P, for A and for C were projected. We can do this in a second. But this is more than saying I can choose just a short exact sequence. I'm saying for any projective resolutions that you choose for A and C, there exists this guy in the middle, such that this sequence is still exact. And once we have this, we have a short exact sequence. We have a short exact sequence in complexes. And we're going to exploit this to, we're going to exploit that to take to construct these delta functors. Any doubt about this? No question about this? Do you want to try to guess how to construct this guy? This is called, I don't know how to say this in Portuguese, this is a horseshoe lemma that one needs to do. And it's again diagram chasing. I've already wasted time doing the snake lemma. I'll continue doing some animal named lemmas. Anyways, let's not waste time on this. Okay, so, right. So what we need to do is apply our functor f to these guys, and then take homologies of those guys. Okay, so we need to apply and then it's just diagram chasing. F to this exact sequence. And use the long exact sequence that homology gives. Okay. I want to stop here with the abstract nonsense and try to do some actual computations. Yeah, so let's try to do some resolutions in real life. So, yeah, perhaps some examples of left derived functors as push forward of the modules, perhaps. Which is the Gauss rule resolution. Stop right there. Okay, so a digression. So let's say that you have a morphism of rings, of commutative rings. Commutative K-algebras. Then you have a map from S modules to R modules. So I don't know how to call this guy. So perhaps this is a good name for this morphism of rings. And then from S modules to R modules, what is this? If you give me something where you know how to act by S, then you just remember how to act by R by applying F upper sharp. So if you give me M in M and R in R, then you take F upper sharp of R and you multiply by M. This is a guy in S. And you multiply by M. And this gives you a good action of R there. So I'm going to call this functor from S modules to R modules F pullback. Oh, sorry. That's a bad idea. F push forward. The other way around, if you give me an R module and you want to get an S module, and this guy I'm going to call F pullback, is you give me an M and you give me N. Well, S is an R module itself. So I can tensor this guy with S over R. And this now is an S module because S acts here multiplication by multiplication on the right. These are commutative rings. Okay? So this is what I will call the F pullback. And in geometry, if you take the spectrum of R and you take the spectrum of S, then you have a map in this direction that is called F. Okay, so I have this F at the level of topological spaces by pulling back maximal ideals or prime ideals, depending on the flavor of geometry you like. You have this F upper sharp at the level of functions, and you have the push forward and the pull back at the level of modules. So now, these two guys are one is left exact and the other one is right exact. So this guy here is right exact. Because it's a tensor product, we already know this. So this guy here is right exact. This is a tensor product. And I would like to say that this guy is the adjoint. But we've seen that the adjoint, well, this is actually left exact. So I would like to view this as a home. I said that the adjoint to taking a tensor product is taking a home. So what is a home here? What is this functor? Right? So this functor here is the functor that takes the tensor product over R with S, of whatever this is. So this is the tensor with S as an R module. So what is the other functor? Which just forgets the action of S and remembers only the action of R. And it should give me an R module. Did anyone guess? I can only guess one thing, so it has to be correct. So can anyone shoot? É o home GS para M. Isso é a única coisa que... Oh, sorry. So it's home from S to M. This is the only thing that we can guess, that it has to be more or less of this form, because it's the adjoint of S. And a morphism from S to... And it also has to be M itself as a space. And a morphism from S to M, at least on a ring that is as big as S, should depend only on the image of 1 here. So that's M. So now the question is, do I put R or S here? M is just an S module. It's not an R module. So I can only look at S here. And R acts on S by multiplication by F sharp. So this is still an R module. So these two guys are adjoint. And unfortunately, I said that I don't remember the symbols, but I remember the orders. And, well, this guy here is right exact. And this guy is left exact. And it happens because they are adjoint, and they are adjoint in that direction. This is the left adjoint to this guy. So the pullback is left adjoint to the push forward. Okay, so that's one thing. But I want to understand this for D modules, not for O modules. Or so let's take the pullback. Let's compute one pullback. So we've been talking about projective resolutions now, so let's compute a pullback. So we know that to compute a pullback, well, I'm going to take a projective resolution. So I'm going to take this. I'm going to take the affine line. So this is going to be one of my rings. I think I want it to be, and I'm going to be pulling back to a point. So I think I want to take the following. I want to look at k of x divided by x, which is just as a ring. This is just the field k. Okay? So geometrically, this is just a point, the spectrum of k, inside of a line, which is the spectrum of this guy. And in this particular case, it corresponds to the origin in that line. I'm divided by the ideal generated by x. So that's this map F, and this is the map F, like this. Okay. But this is exactly, yeah. I don't remember if I think I'm mixing. No, I think I did it in the right. Okay, so good. So now, what I want to take is a module here, and I want to pull it back there. And, okay, so I'll take the following. So I want to take the following sequence of modules. I want to understand what they are. So I'm going to take k of x, x inverse. Actually, I want to do a couple of them. And I want to look at the quotient of this. Oops, the other way around, sorry. So these are regular functions on the line to functions that have a pole at x is equal to 0 to, well, the quotient. Regular functions divided by functions that have a pole. Functions that have a pole divided by regular functions. So these are all modules over the ring, over this ring here. I know how to multiply by x on this guy. And the map is just the inclusion everywhere. And I want to also look at this thing. I want to look at k of x divided by the x. Now this is a module over k of x, which is obtained by this sequence by multiplication by x. So these are the two sequences that I want to analyze. And this is the surjection. Okay, so here this is multiplication by x. The quotient is k of x divided by x. This is just our field k. And these are all modules over k of x. So this is this is a sequence, this is an exact sequence in k of x mod. And this is an exact sequence in k of x mod. Okay, so let's take the pullback under the inclusion of the point into the line. Right? So again, the pullback functor for this map, this f pullback, is the functor that takes tensor product over k of x with this thing. So this is my functor, and this functor goes from k of x modules to k modules, just to vector spaces. And now I'll do a trick that I haven't said today. So in order to compute this, what I'll do this in the following lectures, I'll justify this trick. But I want to do this once and for all for this so that it works for every object. To compute this, the pullback, right? So this is a right exact functor. To compute this thing, evaluate it at every object M, the rule that I said is very simple, is first resolve M, which might, for all these examples that I did, it already comes like that, so we can use this, the definition. And second, apply by projectives. And second, apply this pullback functor to all this. And then third, compute homology. So that was what we needed to do. But in this particular case, where this functor looks like this, like a tensor product, we can resolve this guy instead of this guy. So another way of computing the same thing is you grab M, well, let me give you the procedure. One, resolve S. In this case, it's k of x over S as an R module. So you take S, which is an R module, and you take a resolution in the category of R modules by projective R modules. By projectives. And this resolution works for every M. You don't need to start looking for a resolution for each M. Once you resolve this by projective as an R module, just suppose that you have this P to S. Now if you give me M, you can tensor this guy over R with P. And take the homology of this. And the statement that I haven't proven, but is true, is that the homology of this is the same thing as the homology of resolving M. Let me say that I take a resolution of M, tensor over R with S. Okay? So you can resolve either one or the other one. I'm going to prove this in the coming lectures, but now I'm going to do this in these geometric settings. This one works better. Because once we found one resolution, which is this P, it works for every M. The other way around, for every M that I want to compute the derived functor, I need to find its resolution, and that's tougher. Okay? So once I found one resolution S, it works for every M. Okay, so let's resolve our S. This we have. S is 1, so it should work for the two exact sequences that I wrote there. So our S is this ring, which is just the field K, but I want to resolve this as a K of X module. And this is a resolution as a K of X module. This works. This is P0, which is free as a K of X module, therefore it's projective. This is P0, well, P1, which is itself free as a, and then P2 and so forth are 0. So this is a good resolution of S as an R module. Okay, and I wanted to get the pullback of this guy, which is an R module. So that's known as a skyscraper shift. So geometrically, again, you have the point. We're viewing the point inside of A1. We're taking K. Let's call this I. I think I'm calling F, that injection. Then the push forward of this guy is this shift here. It's this module that is supported at x is equal to 0 in the line, and I'm pulling it back. So what I'm doing now is I want to compute the pullback of that module. But I want to compute the derived pullback of that module. In order to do that, I needed to resolve my S, which I already have, and then I need to tensor it with M. Well, the module that I'm tensoring with, it's this guy itself. Is it clear? So I have this guy as a K of X module, and I want to pull it back by S. So I'm going to take the tensor product of, so this is what I want to compute, K of X divided by X, and I have my projective resolution, K of X, K of X, and I'm going to tensor it. This is the resolution. So I'm going to tensor it with what? Well, I need to tensor it with the module that I want to pull back. In this particular case, I want to pull back this guy, the push forward itself. So I'm going to tensor it with that. I'm going to take this tensor product here, K of X divided by X. And I'm going to take the tensor product, K of X divided by X, over K of X. And then here I'm going to have 0. Okay. So now, so this is in degree 0, this is in degree 1. What are these tensor products? Okay. So, well, this thing here is over K of X, this thing here is over K of X. So both of them are just K of X divided by X. This is K of X divided by X. So this is just K. This is just K. What is this map? The map came from multiplication by X, but X is 0 in K of X. So the map here is 0. So this is 0. I had 0 before, and I had 0 before. So what we see is that the pullback of something that simple as just the skyscraper shift with support at the origin is not concentrated in 1 degree. So in degree 0, we have K, which is something we expected. We started with K in degree 0 here. We put it on the line. We pull it back. We wanted to get back K, but we got something more. We got K in degree minus 1. Well, in degree 1. Okay? So this pullback here is K plus K. It's K in degree 1 plus K in degree 0. Okay? And these are as K modules. So, well, when I write this, I mean L1F of F push forward of K is equal to K and L0 push forward. We know that this has to be the push forward, and the push forward of the pullback is the original shift. It's just K. So that's the simplest example of one functor, which is this F push forward. But before I remove this, I want to notice something that is happening now in the affine setting. This functor here, at the level of modules, is it exact or not? This S is a projective S module. It's a free S module. So this functor, hom S dot, is exact. It's not only left exact, it's actually exact. This push forward here is exact. I didn't need to derive this guy. I'm going to talk about derived functors of left exact functors later, but I didn't need to derive that guy. That guy is already exact. And I apologize that I'm giving really trivial examples, but I think it's just easier to understand these trivial examples. So let's do this other one, which is not entirely trivial. So this one, again, is going to be the pullback for the same sequence. So these are modules on the line. So these are k of x modules, and I'm going to be pulling them back to the point. Okay? But now the difference here is that these are not push forwards of modules on the point. They are push forwards of modules on the point, but in different categories. So these are not coming from a module that has support at x. Okay? So let's pull this sequence back to k of x. And now I'm going to, so in the previous case, it didn't matter if it was m or this, because I was pulling back this guy itself. So I could consider this as a resolution of S or as a resolution of M because I was taking M equal to S. But now it's different if I take this a resolution of M or a resolution of S. Since I already have a resolution of S, I'm going to use this resolution. Okay, so I'm going to tensor this with this over K of X. So again, this is right. So I'm going to do that. Let's take that sequence. I have k of x, x inverse, divided by regular guys. So this is a k of x module. The multiplication is here in k of x. And I'm going to tensor this over k of x with k where x has a 0. Okay? So this is right exact. So this sequence is still exact at this stage. I'm going to tensor k of x, x inverse with, for k of x again, with the point, k of x divided by x. And I'm going to tensor k of x over k of x with k of x divided, oops, this, I was stupid. I am stupid. Okay. By x. This is not what I wanted to do. This is not what I wanted to do. I wanted to pull back this guy. And for that, I need to tensor with the resolution of S, which is this. But still, let's do that. Let's do that pullback. Because we've seen that the functor of pulling back is this functor, which is the tensor by this guy. So let's see what are these, the three guys here. We still have time to do the proper pull. So what is this tensor product? Right? So here x kills anything. So this is just k, and x acts by 0 here. How about this module? As a k of x module, what is this thing? Okay? This thing, as a k module, as a vector space, is what? It has a basis, which is x inverse 1 over x. Sorry, 1 over x, 1 over x squared, 1 over x cubed, and so forth. So that's this as a vector space. Right? So I'm taking things with a pole, modulo things that don't have a pole. And actually, all of this, for every vector here, there exists a power of x to the n that kills this guy. So this is known as the module of delta functions. So these are delta functions at 0 in the line. Because it's freely generated by one guy, which is this, such that x times that is 0. So I'm going to call this guy delta of x. And what does it satisfy? Delta of x times x is equal to 0. And every other thing comes as a derivative n times with respect to x of delta of x. So this is a module over the ring of differential operators. So these guys do not commute. X, this is a non-commuted ring that has d by dx commuted with x being equal to 1. This is a module that is freely generated by one guy that's satisfying this equation. That's called the G module of delta functions at the origin. This is typically the defining equation for the delta function. Okay. But moreover, any object here is x times another object there. Okay? So for any guy here, it's always x times something else. So if you give me any guy here, it's a linear combination of guys like this. Take one of them, it's x to the minus n. And x to the minus n, you can write it as x to the minus n minus 1 times x. And since you're tensoring over k of x, this is the same thing as moving this x to the other side, and that's 0. So this tensor product is 0. The sheaf of delta functions, which is this whole thing, which is infinite dimensional, pulled back to the origin is 0. This is not surprising because already this guy is 0. This is the ring of functions on the whole line minus the origin. And if I pull back this to the origin, I get 0. Same argument. This is the module of functions. Any guy here is x times something. X is invertible here. So any element here is x times something else. So if you write f, this is equal to f times x. Well, f is a bad idea because I use it for something else. So if you have some polynomial here, you multiply it by x and you by x inverse and then by x. This is equal to p. And now move the x to the other side and x is killed here. So this is also going to 0. So if I pull back this guy is 0. This is not surprising because pulling back is right exact and this guy already was 0. These were functions away from the origin. And this is non-zero because this is just the point. Oops, by x. Now, pullback is not exact, so I expect this to, well, there should be a long exact sequence. And I've seen that this guy was already 0, this is already 0, so I need to have something here that is maps isomorphically to this. So whatever I have here cannot be 0. Okay? Because the long exact sequence of taking the derived pullback, which is the derived tensor product by this guy, should be long exact. In particular, since I have here 0, I cannot have here 0. So I already know that the derived pullback in degree 1 of the delta functions is non-zero. Divided by k of x is non-zero. Moreover, I expect it to be isomorphic to this. Right? If it's not isomorphic to this, then, well, we're going to have to, whatever this guy is, it comes with a map to here. And since this has to be exact, the image needs to be everything. So this map should be surjective. This map is 0, therefore this map should be surjective. And, well, we can compute this guy. The pullback with respect to this guy. Well, it's not surprising that this guy, completely derived pullback, is going to be 0. So what I'm going to get is that this guy is isomorphic to this and all the other ones are 0. Let's compute that. And then we'll finish. Actually, let's use this for. Okay, so this is what I want to compute. I want to compute the derived push forward pullbacks of this guy. And for that, I'm going to use the resolution that I already have for S. So what is the resolution that I have for S? I have k of x divided by x. Then I'm resolving it by k of x, which is free, k of x, which is free. And here the map is a multiplication by x. This is my ring S. I am trying to pull back. This is a resolution. Stops here. I am trying to pull back this module, which means tensoring with this guy. And tensoring with this guy is the same thing as tensoring with this resolution. So I'm going to tensor this with k of x, x inverse, divided by k of x, over k of x. So this is this guy itself. And I'm going to tensor this over k of x, x inverse, divided by k of x. And again, it's over k of x. So this guy is still the same as this. But the map here is multiplication by x. So this is delta functions, k of x. This is the map multiplication by x, and it's x inverse over k of x. And I want to compute the cohomology of this complex. This is in degree 0, this is in degree 1. What is the kernel of this map? Well, what are the things here that get killed when I multiply by x? There's only one such thing. 1 over x gets killed. Anything else, so this is in the kernel of the differential. Because x times 1 over x is regular, which is here that I'm killing it. So this, which was my delta function, is the kernel of this map. So the dimension is 1. This is the kernel of this map. This was 0 here. What's the co-kernel of this map? Well, what are my things that are multiples of x? Everything is a multiple of x here. So the co-kernel of this map is 0. Okay, so we've computed that the L0 pullback of the module of delta functions, k of x, x inverse, divided by k of x, was 0. Good, we already knew this because this is the pullback of the same thing. And we already computed that this guy was 0. Sorry, here, that this guy was 0. So the pullback of this, we already knew that this tensor product was 0. This is a right exact functor, so we expected this 0 here. But now we found a one-dimensional space here. So this is saying that L1 of pullback of this module of delta functions is C. It's generated by one guy. As a module over k of x, well, no, as a k vector space, it's just k. And that's exactly what this guy is. So we have k here. Now, this map here should be surjective, because this was a long exact sequence. And since they have the same dimension, it has to be injected. Therefore, I already know that the L1 pullback of this guy is 0. So L1 pullback of functions away from the is 0. Okay? And Ln pullback of anything beyond 1 is 0 because S itself has a resolution of length 2. Since I can compute this pullback by this trick, by resolving S, I'm going to use this projective resolution. P2 is 0 already. So nothing will have homological degree more than 2. So let's collect everything here. And we've already computed everything. We've already computed, therefore, Ln of functions away from the point. So this is the pullback of functions away from the origin is equal to 0 for every n. Well, actually, this doesn't need n. This is 0 for every n bigger or equal than 0. This guy pulled back to the origin is 0 at every n. This is even derived 0. Well, the support of this thing is away from the origin, so this is not surprising. Ln pullback of the ring of delta functions, not the ring, I'm sorry, the module of delta functions. This guy is an example where the pullback itself is 0, but the first derived pullback is not. And Ln pullback of, k of x, the ring of all functions. Well, we've already computed this. This is functions on the whole line. If I pull them back to the point, I just get the fiber. And indeed, this is k. K when n is equal to 0, which are the functions on the point, and 0 if n is bigger than 0. Okay, so we've computed all of those today. Yeah, I'm sorry that I've chosen a really trivial example. Perhaps I'll do some smooth case later on. But I think this should be very clear. Modulo the fact that I took the liberty of changing which of the two factors I resolve. But this is a very simple argument to check that you can resolve either of them.